Keep in mind though, however, homework 7 is also due. Homework 7 is atomic physics that Tuesday evening as well. And don't forget, many of you have not submitted your project draft, so I'm assuming everybody's work getting crunched on that. Keep that in mind, yeah? What you should be paying attention to, however, is on that Canvas homepage, it tells you your final project, final version, November 12th. So it's coming up soon. There's a 2-week window between the draft and the final copy. So if you haven't been keeping up with the homework or the project, you've got a rough couple of weeks, but I believe you can do it. Put your, put it to the grindstone, yeah? Get crunching. Time to clock in. Right. So, makes sense? Know what's going on? What questions you got for me about the next couple of weeks? Yeah.
So the final is probably just due on the 12th, you said, right?
November 12th is when your final project
So that's Tuesday,
presentation.
right?
Yes,
So
Tuesday evening.
on that Thursday in lab, is that when we're gonna start our presentation?
That's going to be one of the first weeks. Yes. So that'll be the first week, and then the week after that will be the second week. The week after that is Thanksgiving. The week after that is our last experiment, and also the last exam for you. And then the week after that is finals.
And tomorrow is the last day to drop with the W?
And tomorrow is the last day to drop with the W. Yes. But remember, just do the project and your grade will dramatically go back up. Yes?
Yes.
Play with the what if grades on Canvas. Speaking of exams, right? I mentioned this last time, I didn't mention it now, but you do have an exam 1 week from today, covering chapters 39 to 41. That's quantum physics, quantum mechanics, and atomic physics.
So are you gonna have 3 questions or 4?
I mentioned it last time, so here it is again. I'm going to repeat it. There are 4 questions I'm anticipating to ask you. The first 2 questions will be from quantum physics. One will be on Heisenberg's uncertainty principle, similar to the ones we did in class. The second one will be the photoelectric effect problem that we did in class. So go take a peek at those problems and make sure you know how to do those. So that's 2 of the problems. The third problem is going to be your quantum mechanics question, which is I'm going to give you a Schrodinger's equation, I'm going to give you a wave function, substitute it in, and solve for the energy levels. You've seen that 2 times now in practice in class. You just have to do it. And the fourth question is going to be from atomic physics. I will show you how to do that problem at the end of today's lecture, which I promised last time. Good, so 4 questions, 2 from quantum physics, 1 quantum mechanics, and 1 atomic physics. Don't forget, you need to bring a calculator, it's very important, and also make sure you bring in your own notes page. You get a whole 8.5 by 11, front and back, write whatever the heck you want on there, whether it's a cool little picture, a little poem, a prayer, whatever you want to put on that piece of paper is okay, as long as it helps you out in identifying how to solve those problems. Yep. All right, I think that covers it. Any other questions you might have about the next couple of weeks? Not yet? You know how to get a hold of me, right? Send me an email, stuff at office hours. I don't bite, yeah? All right, we're going to finish up atomic physics today. Yeah. Last time, we did a quantum approach to the hydrogen atom because, long story short, while Bohr was successful in doing a semi-classical approach, it was not very successful in doing a lot of other things that we observed after the fact. So then we said, well, we got this thing called the Schrodinger's equation. Let's try to find out a wave function and then see if we can find any more information about the hydrogen atom. Long story short, when you come up with the spherical polar coordinate version of Schrodinger's equation, and then you solve 3 differential equations as part of that wave function, you get 3 different results. The first result is number 1. When you solve the radial differential equation, pops out the energy equation. Identical, by the way, to what Bohr predicted. Very amazing feat. Not only does it pop out the energy levels, but it also popped out several quantum numbers that match the boundary conditions for your 3 coordinates, right? The r, the theta, and the phi. And that's why we have three quantum numbers. You have n, which is the principal quantum number. It denotes your energy levels allowed for the atom that you're dealing with. You have an L, which is the orbital angular momentum quantum number. It is a mouthful, right? But it's a number related to the angular momentum, as we will see in a second. And it has a specific set of values. Remember, you start counting at 0, and you increment by 1 until you go to n minus 1. And of course, if you solve the phi equation, you get a third quantum number called the orbital magnetic quantum number. Yeah? It has a set of rules as well, just like L does, where you can only go from negative L to L, and you increment by 1 at a time. As a reminder, these rules for your three quantum numbers come from the boundary conditions. That's why you cannot have any numbers outside of these rule sets, because then your wave function no longer matches the boundary conditions, which means it no longer matches the physics problem you're trying to solve, which is a positive nucleus and, let's say, 1 electron for hydrogen orbiting around. Not literally, right? Because we deal with the electron cloud with the quantum mechanics approach. All right, so you get three different quantum numbers with different rule sets. And then, we didn't talk about this last time, but it turns out another result by solving your theta and your phi differential equations is not just the quantum numbers, but it tells you some physicsy information about the hydrogen atom. For example, if you were to solve the differential equation for theta, that was the second one, right? Out pops out an equation for capital L, which is the orbital angular momentum. In fact, it's the total orbital angular momentum, as you'll see in just a moment. Essentially, it says you get to plug in L, your orbital angular momentum quantum number. So if you plug in, let's say, L equals 0, you can see that you're going to have 0 times 1, yeah? And 0 times anything else gives you an angular momentum of 0. Hey, this should actually be very interesting to you because Bohr says in his claim with the semi-classical approach that the angular momentum should have been 1 h bar. Remember, mvr was equal to n h bar, it was quantized. He says that the lowest amount of angular momentum should have been h bar. But quantum mechanics says, you were a little wrong, Bohr. Truthfully, it's actually 0. And the lowest state possible with no angular momentum is the first possible condition. Obviously, you can plug in different quantum number of L's into this, and it will predict all the different possible orbital angular momenta. Yeah? What's really interesting about this is it's actually telling you that it's quantized. There's only very specific values of angular momentum that your hydrogen atom, or spoiler alert, any atom can have. If you were to solve the phi equation, you get now a formula that predicts a component of the angular momentum. You use the ML, the magnetic quantum number, instead, multiplied by h bar, and it tells you all the possible components that are allowed to that angular momentum. How can you visualize this? Ignore spinning an angular momentum for a second. Think back to physics B4A. Yeah? If you have a force and you exert it at a particular angle with respect to the x-axis, you know that this force is the magnitude, it's the total force, right? And if you wanted to find the x component of it, you would take f and multiply by cosine of theta, right? You could also do f sine theta to find the y component. As you're in dynamics and many physics classes, that's easy for you to understand now, yeah? I want you to think about, ignore the exam, David, ignore the exam. I want you to think about that being applied to angular momentum. Angular momentum is also a vector. So it has a total, that's the magnitude part, like the hypotenuse of your triangle, if you want to visualize it like that. And it's also got one component of it as well. What the quantum mechanics says is that both the angular momentum total, L, and the component to the angular momentum are both quantized. You can't have numbers in between, yeah? But you have very set specific values of its angular momentum. I told you last time that there's a physical representation of your n, l, and m's, right? They're not just random numbers, they tell you something physical about it. N tells us the allowed energy values, L tells you the shape of the electron cloud probabilities, and ML, the magnetic number, tells you about the orientation, the rotation, if you want to think about it, of your probabilities. If you think about that for a second, it actually makes a lot of sense why your LZ depends on the orientation, right? The magnetic quantum number depends on orientation. That's going to be a certain value in a particular direction. So we have two different things of angular momentum. Yeah, you could apply like we did earlier, right? Draw a triangle, figure out the x component, or in this case I'm doing z, but it doesn't matter which direction it is. And you could actually measure, physicists have measured the angle that the electron or atom as a whole has with respect to a particular axis. How many degrees is it rotated from a particular direction? That's what the cosine theta here represents, yeah? But it's the same process as analyzing some kind of force vector. What does it mean to have an angular momentum quantum mechanically for a hydrogen atom? You probably know from physics P4A, maybe dynamics, whatever, that when things rotate, they have an angular momentum. If you're an ice figure skater and you're going around like this, you have an angular momentum, right? So the interpretation here is that because your hydrogen atom has not only a component but an overall angular momentum, you can imagine, careful, this is not technically correct, you can imagine as a concept that the electron is essentially revolving around the nucleus. It's moving around in a circle around that positively charged center. So because the electron is orbiting around, kind of like the planetary model, it's going to have an angular momentum associated with it. How much angular momentum? You can calculate it from the quantum numbers. Yeah? That's the interpretation. Now this is technically incorrect, okay? Because it turns out electrons, as we currently know them, are point-like particles. They are point masses. There is no structure, there's no volume to it. It's a teeny tiny little dot. So that teeny tiny little dot cannot be allowed to rotate, yeah? All right, so this is the new stuff for today, right? Some extra things pop out as a result of analyzing all of your conclusions from solving those wave functions. Let me ask you what questions you got about your quantum numbers, your angular momentum, either total or in the particular direction. Questions you guys so far? So far so good? Right? I hinted at this last time, because if you've taken a chemistry class, you know that these are not the only three quantum numbers that exist. There's actually a fourth one that is often talked about. However, it turns out that the reason we got these three quantum numbers in the first place was solving Schrodinger's equation. We did what we were supposed to do to find out the results of the hydrogen atom. It turns out, a very bright physicist by the name of Paul Dirac came along and recognized that, well, my electron's moving pretty darn fast in an atom. I mean, you can even use Bohr's calculations to figure out approximately how fast an electron will be moving around in orbit. I told you a couple million meters per second. So it turns out he had an idea. Paul Dirac took Einstein's special theory of relativity equations, which we are going to talk about starting next week, and he borrowed the results for relativistic effects. When you have to deal with things moving very fast according to the speed of light, you got to use relativity. Okay? He borrowed Einstein's concepts of relativity and he combined Schrodinger's equation, because it turns out the Schrodinger equation we've been dealing with is for non-relativistic effects, things that are going slow, like baseballs, right? And even electrons that are moving 1,000,000 meters per second, slowish things relative to the speed of light. So he does all this crazy math, and he comes up with his own equation. It's called the Dirac equation. Go check it out if you want to have some nice material to allow you to fall asleep at night, yeah? The Dirac equation is essentially Schrodinger's equation, but the relativistic version of it, okay? What does that mean? Well, if you solve it, very similar to how we solve Schrodinger's equation for the hydrogen atom, there's something really important that pops out, which is actually a property of the particle that you're dealing with, which is what we call spin. Spin, the fourth quantum number that pops out, is actually a solution from the relativistic version of Schrodinger's equation being applied for that hydrogen atom. Now, long story short, spin is treated almost exactly the same way as your angular momentum. You know earlier, we just discussed this, that if you have a planet or a ball that revolves around some nucleus, like the sun for example, in a planetary model, it has an orbital angular momentum. Orbit meaning going around, yeah? However, spin can also produce an angular momentum. I want you to imagine having a baseball in your hand. Baseball sphere, just rotate it around, right? Rotate it around in the circle. If something rotates, like your figure skater, it also has an angular momentum. How much angular momentum? Well, Dirac says you can calculate it. Here's capital S. Capital S is the spin angular momentum. Yeah, that's what the S is. It's still angular momentum, but due to only the spinning nature, yeah, just the rotational nature. It depends on this new quantum number called S, which is spin. Yeah? So S is just the spin quantum number, just like over here L was the orbital angular momentum quantum number. It's just a number. And it turns out amazingly, when you solve Dirac's equations, it only has a one quantum number, ever. It only ever has a spin of a half. It does not have any other number associated with it. It's a little bit different than the hydrogen atom here, right? For the hydrogen atom as a whole, you can have many different possible values of orbital angular momentum. But for spin, there's only one thing, one value it has. And it turns out amazingly, the spin is an intrinsic property. What do I mean by that? Every object has a specific amount of mass, right? Like the mass of an electron, the mass of a proton. Those are intrinsic to the particle you're talking about. Just like charge is an intrinsic property. Charge of an electron is always the same number, right? All electrons are treated equally. Every electron is treated the same exact way. It's got this new intrinsic property called spin, and no matter which electron you look at, no matter what kind of motion it has this specific intrinsic value, the spin of a half. Here it is, yes? Now, not only can you have a total spin angular momentum, but just like angular momentum earlier, the L, you can have a component to the spin's angular momentum. It's kind of confusing, but use the same concept of the force I gave you earlier. If you have the total force, that is the total spin angular momentum, you can find a component to it, yeah? The component of the spin, it turns out, depends on either one of two different configurations. Yeah? You either have a positive 1/2 as the magnetic spin number, or you have a negative 1/2. Let's talk about the physical interpretation. You know what the interpretation of angular momentum is, right? That's your electron orbiting around the nucleus in a circle. So that's the classical picture, right? Now what I want you to do is imagine not only is the electron just revolving around, but it's also rotating, it's also spinning, like a billiard ball. Imagine a billiard ball spinning while revolving around the nucleus. Yeah.
Wasn't there a similar concept for that planets are revolving around the sun, but the entire solar system is also moving towards that direction?
Sure, there's always something that's moving in relationship to.
Right.
Yeah. In this case, I'm only focusing on the rotational motion of the electron and, the revolving motion, yeah, and the rotation motion of the electron. I'm not worried about that motion relative to other objects. You're not wrong. Galaxies and systems have a relative velocity between other systems and galaxies. Yeah. So this is how you should physically be interpreting sorry, not physically, this is how you should be conceptually. It is not actually correct. It's a quantum mechanics thing that's purely described by +1/2 and -1/2, yeah? But what you should be able to do is kind of relate it back to an analogy of a real life thing that you can connect it to. I hope you can imagine if I have a sphere that rotates like this, there's a spin associated with it, right? It turns out you can use a right hand rule and you curl your fingers in the direction of the spin, and that means that it has this particular direction. It's oriented upwards. That's where you get the +1/2 spin, yeah? Imagine it spinning the opposite way, yeah? If you use a right hand rule, your spin now points down, yeah? That's where the -1/2 comes from. So it spins one of two ways is the conceptual thing to think about for the rotation of the electron. This is often why we say colloquially, when talking about the spin, it is either spin up or spin down, right? An electron will either have a spin value of +1/2 or a spin value of -1/2, spin up or spin down. Now, I really want you to understand, don't take this literally, because as I mentioned earlier, this spin concept here is purely quantum mechanics. There is no classical analogy to it other than the visualization of using a ball, something that is spinning. So an electron in an atom is not literally doing this. An electron is not literally spinning around a particular axis, because I mentioned earlier, it's a point particle, point mass. Now, there's a difference between a point mass and a rigid object, because this thing you have to consider the entire rotation of the mass, yeah? But for an electron, there is no size, there is no something extended for it to rotate around. This is actually the current theory of an electron. We think an electron is the most fundamental particle it can actually be made up of. There's nothing smaller inside of the electron that we think exists. That's the modern theory. Things could change as more and more advanced physics comes up. Okay, so you have now 4 total quantum numbers to keep track of. You've got N, you've got L, you've got ML, and you've got MS. Make sense? It turns out, not only do all 4 of these quantum numbers describe the hydrogen atom, but they describe all of the other atoms as well, which is a fantastic success compared to Bohr's model, because Bohr only allows you to predict the hydrogen atom or hydrogen ions. As long as you keep track of your N, L, ML, and MS, it can allow you to describe all the more complicated atoms on that periodic table. Pretty impressive, actually, right? You solve one problem, and now you can identify characteristics of all the other more complicated atoms that you're dealing with. So let's do a little bit of a counting session, yes? It's a common question I could ask. Let's assume that we're dealing with a principal quantum number of 2. That means n is equal to 2. I might ask you, what are the total number of possible states that you could have for an electron in an atom, yeah? You can still imagine we're talking about a hydrogen atom. So what you can do is you can start making the list of if n is equal to 2, you follow the rule sets. In other words, what are my values of L that are allowed? You tell me, if n is 2, what are my values for the L, the orbital angular momentum quantum number?
0 and 1.
0 and 1, right? You start counting at 0, and you go up by 1 until you reach 2 minus 1, which is 1, okay? So I'm going to make a tree. I'm going to break up my L equals 0 and my L equals 1, okay? Let's look on the left side first. Let's focus on L equals 0. When your L quantum number is 0, that governs all of your magnetic orbital quantum numbers, ML. So what value of ML can I have if L is 0?
0.
Not -101, you start with this. What's the negative of 0? Just 0, right? Okay, yeah, starting easy. So the only number allowed is the magnetic quantum number of 0, yeah? Orbital magnetic quantum number. And we just said a second ago that if you have a particular value of ml, it can have either spin half up or spin negative half down, yeah? So that means you have two different possible spin states, which means you can have two different configurations of an electron to have. So we're done with the left side, right? We've now identified the fact that an electron can be classified as 2, 0, 0 positive half, or 2, 0, 0 negative half. Those are the set of quantum numbers that distinguish one electron from another electron, two completely different electrons. Let's do the same thing for L equals 1 on the right side of your graph. All right, everybody, here we go. If L is 1, now what kind of values can ML have? Yeah, negative 1, 0, W to 0, and 1, yeah. Negative L to L. So you have three different possible orbitals, is what we say, for your magnetic quantum number. But don't forget, for each one, you could either have spin up or spin down. You have two spin configurations for each of the ML values. So you get two spins when ML is negative 1. You get two spins up and down for ML equals 0. You also get two spins for ML equals positive 1. So if you wanted to distinguish one electron from another, right, or one atom's electron configuration from another, you need the full set of numbers, NL, ML, and S. So you could have, for example, an electron that has 2, 1, negative 1, spin up, positive half, or 2, 1, negative 1, negative 1 half, spin down, and then you do the same thing for the rest of them, right? 2, 1, 0, spin up, 2, 1, 0, spin down, etc. So it becomes a counting game, right? The question is, what are the total number of electrons you can fit in this particular subshell, maybe, right? Remember, L's are when you start talking about subshells, or N's are when you're talking about shells, right? Just as a reminder, kind of weird words that we use, but that's the connection between them. I want you to think back to last lecture. I gave you a shortcut, right? That means that when N is equal to some number, you put that out front, and then depending on your value of L, you give it a letter, S, P, D, F, or if it goes past that, it's all alphabetical after that. So if you had to classify this with your shorthand notation, what would I name this as? What times what letter? Okay, so you do N first, so what's my value of N? 2, and then my L is 0, so what letter does that correspond to? Say it again. S, okay? So I would label the left side as my 2s subshell, yes? Over there on the right side, if I wanted to label this subshell, I would say 2p, because N is still 2, right? Remember, only thing we're talking about is N equals 2 here, just for ease. And because my orbital angular momentum quantum number became 1, so you increase the letter, you go SP, right? P is the second symbol that you use. We talked about this last time, yeah? Someone asked, hey, what about this superscript? Because in chemistry, you're used to being like 2s and a number above an s, right? That number above it is telling you the total number of configurations for that subshell. So here we go, count them up. How many different configurations can you have in the 2s state? How many? Just 2, right? 2 different 2, 0, 0 spin up, or 2, 0, 0 spin down. You got 2 possible configurations. And that means you could replace this as just saying it's 2s2, right? The 2 up here means that you have 2 different possible configurations, or you can pick 2 electrons in that particular subshell, yeah? You could do the same thing with the right side. If you count up the total number of configurations, or states is sometimes what we say, there are a total of 6. You can see 2, 4, 6, yeah? So that means if you're dealing with a 2p subshell, when N is 2 and L is equal to 1, you can stuff 6 total electrons in that subshell. How come? Well, it turns out electrons are a particle that we call a fermion. Dirac derived this from his equation, and he says when you derive something, you can call it whatever you want. Usually in physics, he was like, okay, we'll call it this crazy thing. And in his equation, Dirac describes fermions. Fermions have always a spin half. Yeah? So electrons have a spin half. Other particles that we will come talk to you a little bit later also have a spin half. Now it turns out, interestingly enough, that when you deal with fermions, they can never have the same exact set of quantum numbers. It is illegal if they have the same exact set of quantum numbers. So one electron can have 2, 0, 0 spin up, but no other electron in that atom or in that subshell ever can have the exact same set of 4 quantum numbers. So if you were to throw in another electron, it has to have a different set of numbers. It has to have the other spin. So it gets assigned the -1/2, for example. Yeah? Fermions are interesting because they can never be in the same exact location, the same exact subshell as all the other ones. Yeah? The argument goes like this. If, for example, they all did have the same exact values, they would all be in the lowest states possible. At some point, they would continue to radiate energy, the atom would radiate energy, until all the electrons funnel down to the lowest, teeniest, tiniest state. This is a problem if you've taken chemistry, because you probably remember that you need electrons in different locations for those electrons to actually bond with something else. To have chemical reactions, it's all about the electrons sharing and giving, and that depends on their placement away from the nucleus in different orbits in the shells. So this is why fermions are not allowed to have the exact same quantum numbers. They have to have different quantum numbers, so they occupy different locations in the atom, and also it turns out they have different energy levels in each of those locations.